This week, because I do not have access to R, we'll just be going through the chapter. Chapter 18, Reducing the Dimension in Regression with Multicollinear Inputs, Principal Components Regression and Partial Least Squares. In the previous chapter, we discussed how Principal Components Analysis, or PCA, can help reduce the dimensionality of a data matrix X consisting of n rows and p columns. In some applications of PCA, dimensionality reduction is the only objective, and the knowledge that certain linear combinations are able to explain most of the variability in the X matrix is all that is needed. But more often, the goal is to predict the response Y, and PCA is only a first step of the analysis. Often, there are more predictors than the number of cases, which would make a brute force regression impossible. PCA's role is to reduce the large number of correlated predictor variables down to a smaller and more manageable number of transformed predictors that represent most of the information in the original predictor matrix X. Instead of regressing the response Y on the original predictor variables directly, principal components regression uses the principal components as predictors. Typically, one uses only a subset of the most important principal components in the regression. Note that in principal components regression, the response Y plays no role in determining the transformed predictor variables. One wonders whether an approach that incorporates the response in the construction of the transformed predictors from the very beginning would work better. This is where partial least squares, or PLS, comes into picture. PLS, a regression technique for tough regression problems with many and usually a highly correlated covariates, constructs a set of linear combinations of the inputs in the matrix X for subsequent regression, but unlike principal components regression, it uses Y in the construction of these linear combinations. PLS is widely used in chemometrics, where ill-posed regression problems with many highly correlated inputs seems to be the norm. Like principal components regression, PLS is not scale invariant, so it is common to standardize each predictor column J so that the columns Xj for J equals 1 through P have all means 0 and variance 1. PLS begins by computing for each J the inner product of Xj and the response vector Y, which is theta 1j hat equaling to Xj prime Y. These projections, theta 1 through theta 1p, become the loadings when constructing the first derived input variable Z1, which equals P of J, which equals 1, theta 1j xj. This is referred to as the first PLS direction. We continue this process until k is less than or equal to p directions have been obtained. The regression of the response y on the first k PLS directions describe the PLS fit. If we construct all k equals p directions, assuming that this is actually possible and that the number of regressors p is less than or equal to n, we get the usual least squares fit. Using k less than p predictions produces a reduced regression fit. The k direction PLS k fit is obtained through iterations k equals 1 through big K as follows. We calculate the p by 1 vectors of loading theta of k, theta to the k equals x to the k minus 1 over y, and the n by 1 vector of the k directions of zk equals x to the k minus 1 times theta to the k. Update the PLS k fitted values according to yk hat equals yk hat minus 1 plus the zeta k prime y over zeta k prime times zeta k times zeta k, and unorthogonalize the predictor matrix with respect to the direction zk by transforming each column according to xj to the k, which is xj to the k minus 1 minus zk prime xj to the k minus 1 over zk prime times zk all times zk. So there are 3 examples. First, we'll start with the generated data. We generate an X matrix of n by 400 rows and p equals 100 columns. Each of the columns contains 400 independent, n being with the mean 0 and variance 1, realizations, and the 100 columns are generated independently. The column for the response contains 400 independent realizations from a normal distribution with mean 6 and standard deviation 2. The objective of this exercise is 1, to check that the results of our R program coincide with the results of the function of PLS in the R package Mixomax. And 2, to illustrate that in this example, a PLS with just the first, or perhaps the first 2 PLS directions comes very close to the regression that fits the response on all 100 columns. By using these formulas, we are able to do that. And we can get the R square of PLS using Mixomax with NC equals 2 to be 0.21. The second example is predicting next month's unemployment rate of a certain state from past unemployment rates of all 50 states. We can use the previous data we used from the last chapter. We use the unemployment rates in all n equals 50 US states over a period of 460 months, so from January 1976 through August of 2010. Here we treat this data set as a multivariate, having 50 variate time series spanning 416 periods. Small r, or a large R square in the regression expresses the fact that the explanatory variables are very capable of predicting the unemployment rate for the next month. The PLS results for the first state, Alaska, shows that the regression on the first PLS direction already explained 89.1% of the variation. The regression on the first 2 PLS directions explains 93.3% of the variation. This is already very close to the R squared from the regression on all 200 columns of the X matrix. That explains 99.98%. Note that that last R squared is identical to the R squared we get from the regression on all 200 PLS directions. Then we go on to example 3. Now we're predicting next month's unemployment rate, comparing several methods in terms of their out-of-sample prediction performance. Here we investigate the performance of the following methods. The univariate AR4 model fit to individual series. In this method, the current unemployment rate is regressed on its previous 4 lags. This is done separately for each state. Then the multivariate VAR4. In this method, the current unemployment rate of one state is regressed on its previous 4 lags and the 4 lags from all other states. This amounts to regression on 200 predictors. In total, 50 regressions, 1 for each state, onto the same set of 200 predictors have to be carried out. Component by component estimation is equivalent to the joint least squares estimation, even for a general covariance matrix of the error terms. Then, the VAR4 with lasso constraints. But there is a problem with fitting a regression on so many similar predictor variables is that many predictor variables, perhaps most, are not needed. Regression methods that constrain the magnitudes of estimates may help overcome the problem of estimating too many unimportant coefficients. Lasso methods under several constraint assumptions are evaluated. Then we do the PCA regression and the PLS. The matrix of predictors is high dimensional and its columns are highly multicollinear. This is because lagged unemployment rates of the same state are similar and unemployment rates from different states are alike. Principal components regression, where we regress the response vector on the first 10 or 200 principal components, and PLS regression on the first 10 or 100 PLS directions are being considered. Now we evaluate the forecast on 25 randomly selected time periods, or the evaluation sample. The models are estimated on the remaining 387 observations, or the training sample. Models are fit for all 50 states, resulting in 25 by 50 one-step ahead forecast errors for each studied method. Models are evaluated on the root mean square error that is being calculated from 25 by 50 one-step ahead forecast errors. The random selection of the evaluation and training samples is repeated 50 times, and box plots of the root mean square forecast errors are prepared. The following conclusions can be made. The univariate AR4 model performs well. Its average root mean square error is about 0.13 percentage points. This says that if the true unemployment rate is 5%, the predictions from this model could be off by about 0.26 percentage points. The VAR4 model with its regression on 200 predictors performs worse. Its average RMSE is 0.15. However, one can see that the lasso restrictions will improve the forecast performance. Lasso with S equals 0.25 leads to an average RMSE of 0.11. This illustrates the power of a regularization estimation approach that zeroes out many of the unwanted coefficients. The PCA regression on the first 10 principal components is rather bad. Its average RMSE is 0.33. This implies that we would not need a lot more principal components to predict the unemployment rate reliably. Using 200 principal components gives us the same box plot as the VAR4 model without lasso restrictions. The forecast performance of PLS on the first 10 PLS directions gives us an average RMSE of 0.165. It is considerably better than the PCA regression on 10 components, but it is still worse than that of the sample univariate AR4. We learned that neither PCA regression nor PLS can compete with the VAR4 model that uses some lasso regulations.